like to introduce to you Dr. Tom Bullard. Tom is from the Desert Research Institute out of Nevada, and he has given this lecture for us a couple times. And I really like the way he provides geology information because it's nice, basic overview that everyone, I think, can understand. Because geologists have a tendency to use a language that no one else can understand. It's like, put it in words we can understand, or define the term. So you're going to define words for us, aren't you?
Oh, yeah, sure.
All right, so let's give a warm welcome for Dr.
Okay, I think this might be on your to-do list. It's in the back of your training manual, and it's all about the structure of the earth. It's really down to earth. About that. So probably what will, as you go through the manual, and maybe this is where I might lose a lot of you, but if you go back and reflect on what I'm talking about, it's basically bits and pieces of this article, or this, it's a short overview by Ken Adams, one of my colleagues at GRI. And it kind of covers pretty much all the stuff. There's some newer data out there that's just come out in the last couple of years that I didn't have the last time I gave this talk. I'm not really going to go into it, but we have some of that. So let's see here. Okay, so I'm just a little bit of background for those of you who don't know anything about the Desert Research Institute. We're the nonprofit research arm of the University of Nevada system. We're soft-minded. We go out and hustle our own money to keep ourselves employed. It's been a challenge. I'm a geomorphologist, and the soil geomorphologist is sort of what I do. That means I study the landscape, the landforms that are out there. I understand how they form, the processes, the forces governing the processes that actually end up looking like something that you recognize. I've spent a lot of my time in the desert lately, so I don't claim to be the expert on Lake Tahoe. But as a geologist, I can kind of say anything and be anybody I want to be. So, where do I just aim it anywhere?
Well, the thing is over here, yeah.
Yeah. Okay, so what I thought I'd do is I kind of get us into the framework of where we're at, just besides being here at beautiful Incline Village. Talk a little bit about the geology and tectonics, some of the faults, and the evidence for them, and that's been in the news recently in the last several years. Another great phenomenon is McKinney Bay and known as the McKinney Bay landslide complex. I'll talk a little bit about the ice ages and some of the ancient shorelines. I'm not going to talk about lake levels. I think that will be for somebody else to deal with. I'll talk about ancient lake levels, but not since the gates went in. Since the gates went in, things have been pretty relatively stable. Okay, there are lots of different ways we can talk about this from a geologic perspective. We can take the big picture. We're going to have to look a little bit about this and some of the deep internal forces that produce some different rock types and spectacular landforms. This is not Lake Tahoe. Or we know we can talk about the glacial history of this basin, because a lot of the topography we see, particularly on the west shore, reflects the glacial history. So here we go. Where are we? Well, here we are. This is a physiographic map of the United States, and you see Lake Tahoe is right on the edge of the Great Basin, and this part is the Basin Range section, and the Pacific Mountain System. And that has the Oregon Coast Ranges and then the California Coast Ranges plus the Sierra Nevada. So we're sitting right about there. Interesting place to be. Right at the edge of two major physiographic provinces, all sorts of things are happening here. And as we all know, the weather comes tearing through here with great gusto. All right, if we talk about plate tectonics, and if for those of you who may not be all that familiar with what plate tectonics refers to, again, the Dozen Training Manual has a nice little summary of this. But just think of the outer rigid shell of the Earth, the rigid crust of the Earth is broken into a number of solid, relatively speaking, plates and numerous little tiny, smaller microplates. And they kind of move around, driven by the internal heat engine of the Earth. Heat comes up from deep within and rises and pushes, makes new rock and pushes rock out of the way. And this is like a giant game of bumper cars, where they run together, strange things happen, lots of fun things happen, and this is no exception. So, we'll talk a little bit about that plate boundary, but what I want to do is just sort of also put this in a perspective of, has it always been like this? Well, common sense might tell you that no, it probably hasn't been like this all along. But if we look at Paleozoic time, a couple hundred to 500-600 million years ago, this is us, more or less, in this general area. We were in an ocean. Here's a cross section coming across a continent like this, and we would be out here, out in this area. So these were big seas and so forth. Sierra Nevada didn't even exist then. Fast forward 80 to 100 million years or so again, and off of North America, we have what's known as a subduction zone. This has happened several times throughout Earth history on the western margin of what came to be modern North America. Subduction zone is where oceanic crust, if we think about the tectonic plates again, the crust they're made up of is relatively light, buoyant, low density, granitic terrain, and the oceans are underlain by what are known as oceanic basalts, which is very dense, iron-rich rock type. It's got a density of, depends exactly where you're at, but 4 to 5 grams per cubic centimeter. Whereas the granitic crust is around 2.8, somewhere in there. So it's, relatively speaking, one floats on top of the other. Well, as I told you, these plates are kind of being driven around and playing bumper cars, where you have two plates come together. The heavier oceanic crust, when it bumps into the light continental crust, it'll sink beneath it. This is what we call a subduction zone. And as this slab sinks, the deeper it gets, the hotter it gets. All the forces, the pressures, what we call the geothermal gradient, as you go down into the earth, how much it heats up. And it begins to melt, actually, in the slab. We call this thing the slab that goes under. It melts, and magma is produced that begins to rise and then puffs out as volcanoes. If you go a little farther to the north, in the Cascades, we have active volcanism because we have a subduction zone there. You go around the Pacific Rim, we call it the Rim of Fire, you see the same kind of thing. And this, where we're at, a little different story. So here's what we call the Sierra Nevada batholith is being in place. As this magma rises, it's melting, kind of melting its way up. It's like a hot probe in ice. It melts its way up, and you develop a very granitic-rich body of rock there. And that subsequently became the core of the Sierra Nevada. Subsequent to that, 20 to 30 million years ago, this subduction that was happening beneath California, south of Cape Mendocino. It was happening, but there was a more buoyant mid-oceanic ridge that intersected that subduction zone. And when you have something that's hot and buoyant and it runs into something that's kind of buoyant in the first place, it's just a giant collision. So about 20, 30 million years ago, we have this collision. There's no longer subduction. When that happens, it's like a car wreck. The forces begin to move in different directions. I haven't lost anybody yet. So this is our modern day tectonic setting. It's a little skewed, so north is that way. Here's our star for the Lake Tahoe region. Don't pay too much attention to all these different things, Sierra microplate and all this and that. This is the Pacific plate. This formerly subducted beneath the western margin of North America. Here's a fracture zone. This is what's known as the Gorda plate and the Juan de Fuca plate. These are subducting underneath the Oregon and Washington coast. We call it the Cascadia subduction zone. And so we have active volcanism here. The volcanism through here is, for the most part, ceased. The last kind of gasp, we're in the Lassen, Shasta region. And then there's some younger things out here in the desert. So when we went from basically Pacific plate going underneath North America like this, now it got stuck and it's still pushing, and so it's into a lateral sense of motion we call a strike slip. Yes?
So the Sierra microplate there, is that formerly ocean bottom, mostly sedimentary rock that's been kind of accreted on the
well, you're asking us a tough question. There's not an easy answer for that one. Must be a geologist to use a word like accreted. There is accreted terrain here, there's no doubt about it. The coast ranges you can find subduction complex rocks within the coast ranges. Central Valley has got a lot of Cenozoic, younger, even some upper Paleozoic, or Mesozoic, Mesozoic and Cenozoic rocks within the basin and fill there. So, but what's underneath that? Yeah, it's more crystalline rock. So, in a sense, yeah, this probably would have been some kind of a oceanic at one point. When exactly? I'm not a California geologist, so I can't answer that one. Important thing about this new motion, and you've heard of the right lateral slip on the San Andreas Fault, is that the stress field now has been totally reoriented, and what it's resulted in is extension, or it's pulling apart in an east-west direction. Remember, north is kind of off this way. In an east-west direction across the Great Basin. And that has resulted in the formation of what's known as a basin and range. So we have ranges and basins, and they are bound by structural elements called faults. In this case, there are normal faults on either side of a basin, and the basin drops down, the mountains relatively rise up. I was going somewhere with that. That's okay. Lake Tahoe sits right on the edge of this structural zone. This is called the Walker Lane, or the Walker Lane Belt. And there's a series of stepping systems of what we call Horst and Graben. Horst is basically the high mountain ranges. The Graben is the German for grave or deep hole. We call them extensional because the forces that form them are pulling the crust apart. Lake Tahoe sits right in one of these extensional features, these extensional structure. Earthquakes, sure. Red ones are big earthquakes. These are historic ones, 1852, only up to 2005. So we've missed on here all the big swarms from a couple of years ago, north side of Tahoe. But some of them are big. We've had some great big ones in Nevada, magnitude 7 down here. Southern California. This is getting down to the Mono Mammoth area. What's that?
I was going to say, is that Bakersfield?
Actually, no, that's probably Bishop, Lone Pine, that area. 1870 something or other, big earthquake there. We'll talk a little bit about this, not too much. I don't think you need to frighten people, but if they say, well, is there going to be an earthquake up here? Yeah, someday. When? Who knows? The probability is relatively low, but it's like anything else. The probability of having traffic accidents is, relatively low, but it could happen any day. So, speaking of earthquakes, let me go back to what a fault is. A fault's just a planar discontinuity or break in the Earth's crust along which substantial displacement has occurred. So imagine between my hands is a fault. A normal fault would have a slight incline to the fault plane, and one side would go down, the other side would go up. A reverse fault is just the opposite on the same thing. And if it's a horizontal slip along a vertical plane like this, we just call it strike slip. These are normal faults in Lake Tahoe, and these black lines, the guys in the front, folks in the front can see these. There are lots of them, there's no doubt about it. And it's only been in the last few decades that a lot of interest has been placed on what we call paleoseismology, or earthquake geology, trying to understand earthquake history from faults. And in the last 5 to 10 years, in fact, in the last 5 years, we've got a whole lot of raft of new information, new techniques and methods that allow us to actually determine how much movement has occurred along these faults. So, we talked about rocks. If we look at the north end of Lake Tahoe, most of these rocks up here are tertiary age and quaternary, the last 2.5 million years. Tertiary goes back to so it's everything since the end of the Cretaceous, so 80, 60, 80 million years or so ago. Quaternary is the last 2.5 million. These are volcanic rocks, mostly up in the north side. We have Cretaceous and tertiary granitic rocks. This is part of the Sierra Nevada batholith I showed you earlier. So this kind of pink and some of the brown stuff is more of the granitic rocks. These are granitics up here too, closer to Incline Village. You get another one up there? Yeah. Down here, in this region, southwest part, we have more older rocks, isolated metamorphics. I'm not going to talk about what a roof pendant is, but that can be Q&A. We have quaternary glacial and cluster deposits along the south shore, and a lot of the west shore. It's a lot of this yellow stuff, mostly close to the shore and extending back into the mountain ranges. You see these linear valleys. These are all glacial valleys. We'll talk about that in a minute. We'll talk about a lot of stuff in a minute. Okay, so let's just talk about the north end of Lake Tahoe, because that's where we're at. Oops. There we go. Okay, so here are the tertiary and quaternary age volcanic rocks. Some of these are, they're older than this, but there's some that are quite young, 1.4 million or so. We're over here. This is a thing called they call it the North Tahoe Fault. I think it's now the Incline Village Fault. Came just at the right time. This is known as the West Tahoe Fault, West Tahoe Dollar Point Fault, because it shows up at Dollar Point, and you see all these little, it looks like little splays or like a horsetail, extending onshore in the area of North Lake Tahoe, possibly a cause for concern. It's to the east of there, but it's still up in this area. Our granites. So here's the Dollar Point Fault, and here's the Incline Village Fault. Okay, we're here, and here's the Incline Village Fault. Goes right through almost through the school. If you go over there, you can actually see the fault scarp. Yeah.
So are most of these faults kind of surface cracking as a result of this kind of shearing force that's happening, or are we still seeing?
Yeah, there is some shearing going. There is some shearing going on. When we talk about shear, a lot of times that's more of a strike slip kind of phenomenon. But yeah, there's shearing of the rocks every time you move them. These are normal faults, largely. And yes, it has to do with the extension, among other things. Okay, on the west side, as I alluded to just a few minutes ago, it's a very complex system of faults. The Tahoe Sierra frontal fault systems, basically this whole mess. Geologists, particularly earthquake geologists, love to put names on things. You kind of have to, because otherwise, what are you going to say? Well, it's the fault that's over there by the moraine, that's by the tree. So they put names on them. But this is the kind of one of the biggies that everybody's kind of concerned with, the West Tahoe Dollar Point fault, and then the Inclined Village fault, which is just off the screen here. There's been a fair amount of information that recently has come out of following Lake work that John Kleppe has kind of been a driving force behind. They have some rather spectacular bathymetry of the lake. There are glacial moraines. We'll show you in a few minutes what a glacial moraine is, that are displaced by these faults. If you know how old the glacial moraine is, then you can say something about how recently the fault occurred, or the displacement on the fault, as well as the amount. So it's a very complex zone. Some of these are capable of generating large earthquakes, according to very recent publications that just came out in the last year or so. I alluded to some of the new techniques that are available. LiDAR, this is a laser or light and distance analyzing radar. This is 3 panels of the same thing. This is fully vegetated. This is black and white color, and this is a LiDAR, where it basically strips all the vegetation off, and you can see everything that's hidden underneath there. And then here's at the bottom is a picture. So close I can't even see this, but this is Cascade Lake, Emerald Bay. And these white lines that go across here are traces of faults that they're now able to map. And then they go out in the field and you actually measure the displacement from one side to the other of this fault and come up with what we call slip rates, how much this thing is actually moving. More evidence of active faulting in the area. Here's the West Tahoe fault, West Tahoe Dollar Point fault. And what this is some submarine or submarine isn't marine, but it's I think this is the chirp data. It's basically just sonar that goes down, bounces off the bottom. And it bounces off all these different layers, and what these represent are lake beds. So sediment deposits within the lake bed. And so the sonar goes down and reflects off these lake beds, bounce back to the surface, and they process it and come up with a picture like this. Well, here's a state line fault down in the south end of the lake. And here's the McKinney Bay debris complex. So these 2 green lines represent a formerly continuous surface that now is displaced. So this is one way to get at the amount of vertical displacement across this fault. In this case, it's about 21 meters. This is from Graham Kent and others, 2005. He's been up here to talk quite a few times, so I don't need to belabor that point. I mentioned I talked about the McKinney Bay landslide complex. This is here's McKinney Bay, and you see this kind of all this jumble of these stuff here out on the lake floor. So this is a bathymetric, a nice digital model. Not so much a model, but it's been put together from all the sonar images and so forth. Here's the shoreline, and this is the aqueous representation. So the purple's the really deep stuff, the yellow's less deep. So all these things that are sticking up here are pieces of this landslide mass. We don't really know when it happened. Some people have written that it's about 60,000 years ago. Some say it's around 300,000 years ago. I don't know what the latest is. But this is based on the amount of sediment that's been deposited on top of these blocks. It's like 15, 25 meters of sediment. This fine grained stuff is mostly very fine grained. Sitting on top of these blocks, they ran down a tube and took what's known as a piston core. You drive a pipe into the sediment and you pull it up, it creates a little suction and pulls the whole thing up. They got about 6 meters of sediment. I think they had some datable, datable material in there, but based on sedimentation rates, you can extrapolate how old that might be, how long it took to accumulate that amount of sediment. If you know it accumulates at a rate of X number of millimeters per year, and you have 6-10 meters of it, then you just do the quick calculation, figure out how old this thing is. So it happened quite a while ago. I don't think there was anybody around at the time. There's another close-up of these blocks. I don't remember how big they are, but some of these things are huge. Do you remember, Heather?
Big, I want to say.
Big. House size.
20 stories.
20 stories, something like
Yeah,
that.
they're monsters. And they're not only out in the lake, they're almost all the way across. You can see little pieces that are all the way almost to the east shore. So this thing must have made a big, rather large impression on the landscape. Just that volume of material falling into the water would be this kind of the same effect as an earthquake.
60 feet.
You can't really say it'd be like the Japanese earthquake in Fukushima, but same kind of effect, except here, in the case of one that's happening on the other side of the Pacific, you basically have one big wave that kind of makes its way across the ocean. Here, the water has nowhere to go except from one side to the other. It's kind of like a bathtub. So if you pound it on your bathtub or drop something in your bathtub, the water's going to go back and forth. We call that a seiche effect. And models have said that if estimates are correct on, say, the West Tahoe fault, West Tahoe Dollar Point fault, some are saying that you can generate a magnitude 7 off that and create a seiche of about 10 meters. So then it's just figure out, okay, what's 10 meters above lake level? Where do I need to be? So if you're here, you might be okay here. I'm not sure how far above the lake are we.
No, he's going to be a little bit.
I'm going higher.
So there's a big earthquake. You might want to think, well, maybe I should, hit for high
Check in
ground.
at the director's party spot.
Is there evidence that that seiche actually impacted the north and south ends, or was the impact mostly on the east and west?
I don't think anybody's answered that question yet.
So there's the computer model that you'll see in the movie Lake Tahoe in Depth, where there's an animation of the estimated movement of the water, and so you can watch it in 3D later. But it's based on a computer model. So
People have looked for deposits, similar to what we would look for in tsunami. When a tsunami happens on the coast, you get debris and all sorts of stuff that goes way inland, and lagoons, estuaries are really good places to look for tsunami deposits, because suddenly you're transporting stuff like sand into an environment that's mostly silts and clays. And when you put a core down into an estuary or a lagoon, you pull it up and you have all these fine sediments and then a layer of clean sand, nothing growing in it, no organisms, nothing. And then more fine sitting on top of that. It's a good chance that the sand represents some big event. Could be a flood or it could be tsunami, depends where you're at, how you make your interpretation. So those kind of things should be here somewhere. People have looked down towards the gravel pit south of here. There's a big borrow pit. I haven't had a chance to go in there and look around yet, but there might be something out there.
There is a paper on cobbled dunes that are perpendicular to the coast off Tahoe City.
Well,
And
yeah.
as I remember, it's been a few years, but as I remember, they were saying those could have been created by the sage. And the fact that they were cobbled dunes rather than sand
Yeah.
dunes meant that there was an awful lot of energy.
Yeah, there would be a tremendous amount of energy.
Yeah.
Philip, you're just asking all sorts of questions. All right, this is he's a geologist in the group.
So, are there other landslides of similar magnitude that created a similar debris discharge that we could compare on land? Is this the only one that, I mean, there's so much debris in that water.
Yeah, there's been, well, if you go up to Yellowstone, West Yellowstone in 1957 or so, there was a very large earthquake up there. And if any of you are familiar with that part, West Yellowstone, there's what's known as Hebgen Lake or Earthquake Lake, and a big chunk of the mountainside slid and basically covered up the valley. The Grovant slide, which you can see from Jackson, I think, is actually not from Jackson, but from north of Jackson. You look back and you see this thing. It's a monstrous slide. So yeah, there are other examples. There was the Viant Dam disaster in Italy in the 60s, I think, when a huge chunk of the mountainside went into a reservoir, displaced so much water it overtopped the dam and took out villages downstream. So yeah, there are things to compare it to. Kind of feel like a doomsday guy. Sorry. All right, well, let's go on to something. This seems to be a lot happier. Ice ages, I need a picture of a mastodon or something running around here. Nice shot at Emerald Bay. And snow-covered Sierra. One thing to notice about these is all these little tiny peaks sticking up, and they're all pretty close to the same elevation. And you come down, there are a lot of ridges kind of at the same elevation. You might be able to pick out these U-shaped valleys for those of you that go down to Yosemite and so forth. That's the classic Sierra glaciation. And up and down the eastern edge of the Sierra, you get down to Mammoth Lakes and June Lake, Convict Lake, Bridgeport. You see these beautiful U-shaped glaciers, very looks like Europe. They were once occupied by ice. Well, in the Tahoe area, we've had 3 major glaciations. Within each of these, there are probably many other little advances and contractions. The oldest one, 400,000 to, this is question mark, 600,000. It's really hard to get a grip on what the age of this thing is. The Tahoe, we've got a little bit better information on this, but that's because new techniques for dating the surface exposure age of rocks, in other words, boulders that are residing in moraines. These numbers are a little bit better, but also this could reflect that there were this range of ages for the Tahoe, 65,000, 140,000 years. But there is, number one, climate change, and there are multiple glaciations. And then the youngest one, the Tioga, happened at what we call the last glacial maximum, the LGM. And this is 15,000, 25,000 years ago, right at the end of the Pleistocene. So sea level was way down, and the Earth was covered with a lot of ice. Just bringing you up to speed on some glacial landforms. Here's a couple of really nice pictures, and then here's some cartoons showing about the same thing. But when you have basically an ice cap or really thick ice, all the little tiny bits and pieces are sticking up above it. And when the ice goes away, we're left with these sharp peaks called horns. Moraines, where 2 glaciers come together, like this one right here, and this valley glacier, where it's carrying debris along the edges of the glacier. It's like a bulldozer. Imagine a bulldozer just moving down the valley. Well, it's pushing stuff forward, but stuff is also dripping over the sides of the blade. And even when you see the guys grade the roads out here, what's left behind is always that long trail of positive relief that you try to drive through and you wreck your car. It's kind of a weird analogy, but what you get on a glacier is the same effect, and we call those lateral moraines. Where two glaciers come together, they each have a lateral moraine on either side. When they come together, all of a sudden you've got a common one right in the middle. We call that medial moraine. So here's let's see, what color did I make these? Green. You can't even see it. This black thing looks so nice and inviting is a medial moraine. So somewhere up valley, there are two valley glaciers that came together. And then this is a representation on this cartoon. Same thing right here. Glaciers can block other drainages and create little lakes. They can dam up drainages. And that is important in Lake Tahoe. So Tahoe, what you see around here mostly, what people will be, particularly around Emerald Bay, you're looking at lateral moraines. And I mentioned when just the little peaks are sticking up. Okay, here's Lake Tahoe, and this was the Sierra ice cap. And probably several times during Quaternary, this could be a million or more years old when we had glaciations, where very large parts of the Sierra were completely covered with ice except for the little tiny pieces of the range that stuck up. Mount Tallac is one of those. You know, this scale you can't show everything. But if sometime you're driving down I-80, let's see, trying to think of where it would be. Well, just about anywhere on the other side of Donner Summit, even at Donner Summit. If you get out and you find a good exposure to bedrock, you can actually see striations or grooves in the rock that give you an indication of the direction, at least the linear direction that the ice was moving.
If you go up above Cascade Lake, not heading towards Bayview, but heading towards the Cascade Falls, that whole granite block has tons of the glacial striations. They're everywhere.
Yeah.
That whole zone.
If you go into Yosemite, Tuolumne Meadows, they're spectacular. The glacial erratic is nothing more than a chunk of rock and debris that was carried in the ice, and then when the ice melted, it just basically drops and stays in place. And you see these beautiful polished surfaces of granite with these gargantuan boulders just sitting there. Everybody scratches, I wonder who carried those there. So that was the Sierra ice cap, and that was quite a while ago. So here's kind of a picture of colored white, what it looked like in the Lake Tahoe area. Here's Squaw Creek and Bear Creek. These would have been the glaciers coming out of Squaw Valley and Bear Valley. And so this is the Truckee River coming down here. And interestingly enough, they did, in fact, there's evidence to support the fact that these glaciers came across the Truckee and created a dam, which blocked the outlet of Lake Tahoe and resulted in actually raising the lake of Lake Tahoe. I think right now, I'm going to do this metric. I can't convert to English right now, but outlet is, I think, 1897. And during the Tahoe glaciation, it went up to 1927 meters, 1,927 meters. I got a picture here. Okay, here we go. You can see, this side you can see a lot easier. The red lines, the yellow lines, and the green lines and the blue line. 1897 is the controlled access outlet here at the North Lake Tahoe. 1908 is kind of a high stand during Tioga. 1926 would be during the Tahoe glaciation. This is one that's 70, 80, 100,000 years old. Tioga is 15 to 20, 25,000 years old. And then this is the Donner Lake. Now I know I know that these shorelines are true for a number of reasons, and I've actually seen some of these. You go up near the airport along the river here, you can actually see lake sediments. And little tiny things are just a millimeter or so thick of black and white, dark light, dark light, dark light, very fine sediment. And that's what happens in lakes, and particularly some glacial lakes and so forth. These are annual, we call them VARs. They're just thin laminations because of seasonal variations in temperature and organic debris and matter that's coming into the lake and settling out. You can count these things up, little couplets, and figure out how old they are. Well, those things we were looking at stuff. Let's go back here. We were looking at things that were up here at this 1908. So we're 11 meters, 35 feet above modern lake, and thick packages of lake sediments. I mentioned that the Truckee River was dammed by ice coming out of Bear and Squaw Creeks, and there's some little evidence of this here. What's really interesting is, and you've probably heard of through National Geographic or Discovery Channel, these things in Iceland called jökullips, and these are basically ice dams that suddenly break. Lake Missoula, which had a great hand in forming the channel scablands along the Columbia River, was an ice dam, monstrous ice dam lake that just gave way. Same thing happened here, because as you go down the Truckee River, you will see huge trains of boulders. Trains are just, it's another word for just long lines of large boulders. Some of these are approaching the size of houses and so forth, that have their origin up in Squaw and Bear Creek. We know that because the rock type is different from what everything else around it. Strangely enough, down in Reno and just west of Reno and Verdi, right at the post office, if you're over there are what we call glacial erratics. There are rocks, boulders the size of Winnebagos, that the nearest rock source is up close to Donner Pass. So these things had to, and you can't, there's not water fast enough to move this stuff. So it had to be carried down on blocks of ice during one of these outbursts. Even as you go downstream from Reno into the canyon, heading out towards Mustang, there are big boulder fields of rocks of a makeup that come long ways away. And they're too big to really be transported by even a great flood. We try to calculate the shear stress, and the numbers are monstrous. Water doesn't flow that fast, it vaporizes. So these had to be carried on a raft of some form or another. What was strange is that during that time, the whole Truckee Meadows was almost like a lake. So these things had to go across the lake and down the river. Okay. So I'm just going to show just a couple shots of evidence for higher lake lines, lake stands. Just while I have this up here, this is a perfect, nice little map. This is a geologic map. The colors represent different age rocks. This yellow stuff is all what we would consider quaternary age, so it's less than 2 million years. Most of this is less than a few 100,000. Fallen Leaf Lake, and you almost see a concentric coloration here. Light yellow, dark yellow. The dark yellow is older glacial moraines. The light color is younger. And you see these kind of clothes right here at the end of Fallen Leaf Lake, and here's Cascade Lake, the same thing. These are terminal moraines, and they've basically created a nice little lake basin. Here's our West Tahoe Fault going through Fallen Leaf Lake. That's a no-brainer now. Cuts across here at this time of this map, this scale, it doesn't show. So I'm just going to show you just a couple things for evidence here. Here's so close. What are mapped out here are beach ridges. This is along the south shore, southeast shore, Lake Tahoe, at 1,902 meters. So we're 5 to 8 so meters above current lake level. Over here, Cascade Lake, Emerald Bay, here are the moraines, and these have what are called wave-cut terraces on these moraines at consistent elevations. You can just select bathtub rings. And so these are representing high stands of Lake Tahoe, well above the outlet today. So there was those ice dams coming out of Bear and Squaw Creek that allowed the lake levels to rise. Okay. Also, besides just mapping these topographic features, we can look at the sediments. This is here at Sugar Pine Point. Here we have some clays overlain by glacial till. There's a big rock here. And then this deposit up here is interpreted as beach sands. So these are deeper lake sediments, glacial deposits, and then beach sands. So the only way you can really do that is to raise the lake level. Here's another spot at Ward Creek. You see these little, look like faint lines, kind of inclined like this. This is what we call bedding. And this is the front of a delta. So a delta is a very special kind of delta that forms when a stream comes into a standing body of water. And the way the sediment comes to rest or settles out of the flowing water into the lake will form on the front edge of the delta. It'll form these little slopes and just keeps adding to it. Within that is a tephra, a volcanic ash. It's somewhere between 23,000 and 27,000 years old. And this is 5 to 1908, 10 or so meters above the modern outlet. Here's Baldwin Beach, 1995, modern beach ridge. We find beach ridges up here at higher elevations. So these are older. I'm not sure we know how old they are, but they're definitely older, representing higher lake settings. It's also been lower. It's also been a lot lower, as everybody, I'm sure you all know that. This is 2002, right at the outlet. In fact, it was almost so low that water wasn't coming out of the lake. If any of you were here and went out there and walked around, you could actually walk across the outlet. We know it's been a lot lower. Here's a tree found at Baldwin Beach, about 5,300 years old. How deep is this? Less.
It's
Well,
like
see it pretty
20 or
well.
30 feet.
Yeah.
Yeah.
It's not super deep, but it's deep enough. At Fallen Leaf Lake, there are trees that have been interpreted to be in growth position. There are some people that will argue with that no, these trees they fell stumped down, and that's the way they floated and sank, and the root ball carried them down like that, and the sediment is deposited around them. Others say no, they were in growth position. Anyway, the story there is these things are in, I think it's over 100 feet deep water. John Kleppke has a paper in Journal of Nevada Water Association talks about this. But so these trees in Fallen Leaf Lake were grown above water on dry ground or moist ground between this period, 850 to 1150 AD. So 800,000 years ago. But we also know it died around 1200 AD, so the water came back up and submerged it. Water went down again because the tops of these things are rotted off, and then the lake level went back up again. This is in Fallen Leaf Lake. So there's been fluctuation. The interpretation there is that when the lake level fell, you had the upper parts of the tree limbs were sticking up and they rotted. And I guess you only get that kind of rot in reservoirs and so forth that are fluctuating. Okay, here we go. Well, this one was just kind of left in is how we're interpreting faults and so forth. This you might be able to see this kind of linear-looking feature. It looks a little darker right there. There's a little change in elevation coming across there. topography goes kind of like this. And some people interpret that to be a fault. But there are other alternative explanations. Just during a lower stand of Lake Tahoe, the stream could have cut that. So just because you have a linear break in the surface isn't always an indication of fault. You've got to kind of put all the little pieces together to arrive at interpretation. So here we go. Lake Tahoe's in a structural basin, one of these big gravens defined by active faults. We've got tertiary volcanic and quaternary rocks at the north end of the basin. Probably played a role in the lake formation because we know there are basalt flows that are about 2 million years old or so, sitting on top of the earliest known lake sediments. So that probably created the outlet, dammed the outlet, and allowed Lake Tahoe to begin filling up. And I have another one. I push the right button. Yeah. And we had the glacial damming causing lake level to rise well above what it is today. Droughts up and down lake levels. So it goes is well below the natural outlet. So I think that's it. I've gone over my allotted time, undoubtedly. Question back there?
What caused the big rocks on the east shore, and how old are those gigantic rocks?
Which rocks are those?
Along the east shore, over Sand Harbor, Marcellus Camp.
Some of those, yeah. Some of those is a natural weathering phenomena of granite. What's called spheroidal weathering. And a lot of it has to do with the composition of this granitic rock. It's a very coarse crystalline rock. Now, if you guys, most of you live up here somewhere, and you've heard the term DG, or disintegrated granite. If you pick up a handful of that and look at it carefully, you'll see, well, there's some kind of really clear stuff, and then there's some kind of a little whiter stuff, or pinkish, and there's little flecks of black in this. And then you take that and you go over and look at one of these big boulders. By golly, it's the same stuff. It's disintegrated granite, or grust is the term that I was brought up on. Because granite is a very coarse crystalline rock, and the conditions under which it was formed. This is one of the last rocks, igneous rocks, to form from a melt in terms of temperature and pressure. So it's closest, when you think about it, it's closest to kind of its formation equilibrium. And so it's going to be one of the first ones to start falling apart. The fact that it's coarse grained helps. So you're attacking the mineral grains, and they begin to break down. Sometimes in some of these rocks you can just you can take your fingers almost, but usually a rock hammer and just knock off chunks of DG. Well, as granite weathers, it tends to form these rounded surfaces. Now, my guess is that's what we're talking about. There could be some there could be pieces of old landslide or rock falls that came to rest and now have weathered in place and have taken on that appearance. Another question.
Well, it's actually very similar because I've noticed those rocks too, and a lot of them look like they had a vertical break. And I don't know if that's just like a water going in there and freezing, or I don't know how that happened.
Well, it's a good point because you've touched on two things. One, when these rocks, the Sierra Nevada, formed at great depths below the surface of the earth. We're talking 10, 15, 20 kilometers depth. So they're under enormous pressure. Now, as what we call it unroofing, or as erosion has taken place and you have different density crusts and so forth, the Sierra Nevada are actually still coming up. They're still rising. But erosion's kind of keep it in check, so it's, if we went into a very dry phase, for millions of years we might have a lot bigger mountains. If we went into a very wet phase, we'd probably erode them faster than they can go up. But anyway, you're under huge pressure. As that pressure is released, there are all sorts of fractures that occur within the rock. And those fractures, a lot of times, are vertical and oriented to each other in a direction that represents the stress field under which they were formed. So you can have vertical ones. Then that's a great point of attack for water. So in summertime, it's great. Water goes in there. You got plants that are growing, organic acids which attack the mineral bonds and break things apart. And in the cold season, particularly in the fall and the spring, when you have a lot of cyclic freezing and thaw, put water in these little micro cracks and so forth, and the amount of force that water generates when it expands, when it freezes, is enough to actually break rock apart. And you've probably driven down the highway on a spring day and see rocks tumbling down. Well, those are rocks that have fractured, but they've been held together by the ice. And then when it melts, the gravity takes over and they fall down. But that's a very good point. Water gets into those things and attacks it from chemical and physical processes. Gold star.
All right. Thank you so much.
Yeah, thank you.
Don't feel obligated to memorize quaternary, Pleistocene.
Yeah, good.
But I did want to point to, in additional resources, pages 24 to 52 is sort of that broad overview that Tom was talking about. And then in the exhibit section, the second section of the Thomas J. Long Foundation, pages 59 to 62 is the super short version of just like the 12 main points that we talk about. And we really only focus on the 3 major faults, which are the West Tahoe that goes up through Dollar Hill, and then the State Line Fault, which goes right at the Nevada state line on the North Shore, and the Incline Fault.
Sort of what I do. That means I study the landscape, the landforms. They're out there. I understand how they form, the processes, forces governing the processes that actually end up looking like something that you recognize. I have spent a lot of my time in the desert lately, so I don't claim to be the expert on Lake Tahoe. But as a geologist, I can kind of say anything and be anybody I want to be. So, where do I just aim it anywhere?
Well, the thing is over here, yeah.
Yeah. Okay, so what I thought I'd do is I kind of get us into the framework of where we're at, just besides being here at beautiful Incline Village. Talk a little bit about the geology and tectonics, some of the faults, and the evidence for them, and that's been in the news recently in the last several years. Another great phenomenon is McKinney Bay and known as the McKinney Bay landslide complex. I'll talk a little bit about the ice ages and some of the ancient shorelines. I'm not going to talk about lake levels. I think that will be for somebody else to deal with. I'll talk about ancient lake levels, but not since the gates went in. Since the gates went in, things have been pretty relatively stable. Okay, there are lots of different ways we can talk about this from a geologic perspective. We can take the big picture. We're going to have to look a little bit about this and some of the deep internal forces that produce some different rock types and spectacular landforms. This is not Lake Tahoe. Or we can talk about the glacial history of this basin, because a lot of the topography we see, particularly on the west shore, reflects the glacial history. So, every 100 to 500-600 million years ago, this is us, more or less, in this general area. We were like in an ocean. Here's a cross section coming across a continent like this, and we would be out here, out in this area. So these were big seas and so forth. Sierra Nevada didn't even exist then. Fast forward 80 to 100 million years or so again, and off of North America, we have what's known as a subduction zone. This has happened several times throughout Earth history on the western margin of what came to be modern North America. Subduction zone is where oceanic crust, if we think about the tectonic plates again, the crust they're made up of is relatively light, buoyant, low density, granitic terrain, and the oceans are underlain by what are known as oceanic basalts, which is very dense, iron-rich rock type. It's got a density of, depends exactly where you're at, but 4 to 5 grams per cubic centimeter. Whereas the granitic crust is around 2.8, somewhere in there. So it's, relatively speaking, one floats on top of the other. Well, as I told you, these plates are kind of being driven around and playing bumper cars, where you have two plates come together. The heavier oceanic crust, when it bumps into the light continental crust, it'll sink beneath it. This is what we call a subduction zone. And as this slab sinks, the deeper it gets, the hotter it gets. All of the forces, the pressures, what we call the geothermal gradient, as you go down into the earth, how much it heats up, and it begins to melt. There we go. Where are we? Well, here we are. This is a physiographic map of the United States. And you see Lake Tahoe is right on the edge of the Great Basin. In this part, it's the Basin Range section and the Pacific Mountain System. And that has the Oregon Coast Ranges and then the California Coast Ranges plus the Sierra Nevada. So we're sitting right about there. Interesting place to be. Right at the edge of two major physiographic provinces. All sorts of things are happening here. And as we all know, the weather comes tearing through here with great gusto. All right, if we talk about plate tectonics, and if for those of you who may not be all that familiar with what plate tectonics refers to, again, the Docent Training Manual has a nice little summary of this, but just think of the outer rigid shell of the Earth. The rigid crust of the Earth is broken into a number of solid, relatively speaking, plates and numerous little tiny, smaller microplates. And they kind of move around, driven by the internal heat engine of the Earth. Heat comes up from deep within and rises and pushes, makes new rock and pushes rock out of the way. And this is like a giant game of bumper cars, where they run together. Strange things happen, lots of fun things happen, and this is no exception. So, we'll talk a little bit about that plate boundary, but what I want to do is just sort of also put this into perspective of, has it always been like this? Well, common sense might tell you that, no, it probably hasn't been like this all along. But if we look at Paleozoic time,
I would like to introduce to you Dr. Tom Bullard. Tom is from the Desert Research Institute out of Nevada, and he has given this lecture for us a couple times. And I really like the way he provides geology information, because it's nice, basic overview that everyone, I think, can understand. Because geologists have a tendency to use a language that no one else can understand. It's like, put it in words we can understand, or define the term. So you're going to define words for us, aren't you?
Oh, yeah, sure.
All right, so let's give a warm welcome for Dr.
Okay, I think this might be on your to-do list. It's in the back of your training manual, and it's all about structure of the Earth. It's really down to earth. About that. So probably what will, as you go through the manual, and maybe this is where I might lose a lot of you, but if you go back and reflect on what I'm talking about, it's basically bits and pieces of this article, or this, it's a short overview by Ken Adams, one of my colleagues at GRI. And it kind of covers pretty much all the stuff. There's some newer data out there that's just come out in the last couple of years that I didn't have the last time I gave this talk. I'm not really going to go into it, but we have some of that. So let's see here. Okay, so Just a little bit of background for those of you who don't know anything about the Desert Research Institute. We're the nonprofit research arm of the University of Nevada system. We're soft-minded. We go out and hustle our own money to keep ourselves employed. It's been a challenge. I'm a geomorphologist, and the soil geomorphologist is actually in the slab. We call this thing the slab that goes under. It melts, and magma is produced that begins to rise and puffs out as volcanoes. If you go a little farther to the north, in the Cascades, we have active volcanism because we have a subduction zone there. You go around the Pacific Rim, we call it the Rim of Fire, you see the same kind of thing. And this, where we're at, a little different story. So here's what we call the Sierra Nevada batholith is being in place. As this magma rises, it's melting. The kind of melting its way up. It's like a hot probe in ice. It melts its way up, and you develop a very granitic-rich body of rock there. And that subsequently became the core of the Sierra Nevada. Subsequent to that, 20 to 30 million years ago, this subduction that was happening beneath California, south of Cape Mendocino, it was happening, but there was a more buoyant mid-oceanic ridge that intersected that subduction zone. And when you have something that's hot and buoyant and it runs into something that's kind of buoyant in the first place, it's just a giant collision. So about 20, 30 million years ago, we have this collision. There's no longer subduction. When that happens, it's like a car wreck. The forces begin to move in different directions. I haven't lost anybody yet. So this is our modern day tectonic setting. It's a little skewed, so north is that way. Here's our star for the Lake Tahoe region. Don't pay too much attention to all these different things.